Hello, and welcome to Astronomy 100. In this video, we're going to continue our discussion of how the sun produces its energy. In our last video, we described a couple of options that we can explore when it comes to energy production. And the important concepts is to remember that the sun is not burning, the hydrogen of the sun cannot be on fire, and the sun is not shrinking to produce its energy. And what we saw was that the special theory of relativity related to, of course, Albert Einstein, Einstein was able to show that the sun is producing energy through a process that is involving an equation or a formula that is E equals mc squared. In this video, what we're going to do is I'm going to walk you through how that process works and show you the physics behind that. So let's go ahead and get started with our first picture. On the screen here, what you have is a cutaway. In other words, if we could take the sun and have the ability to cut open a section, to peer deep down inside of it. There's a region inside of the sun that I've highlighted right here, and we're going to call that the core. I realize the word core seems very simplistic and generic, but I'm going to show you that it's actually a little bit more complicated. The core of the sun, this actual sizable region right here that extends out a certain distance from the middle, this is the region of the sun where the nuclear reactions are taking place to produce its energy. So inside of the sun, the energy is produced only inside of this one region right here. Even though that energy has to work its way out from the center, that energy is only produced at the core. The reason why this is important is because at the core, there are certain conditions that allow the energy production to happen. And so if you could go down to this one area or this one part of the sun right here, you would find two important things to be relevant. The first thing is the temperature inside of the core of the sun is 27 million degrees Fahrenheit. On the Kelvin scale, that's 15 million, kelvins. So 15 million kelvins, 27 million degrees Fahrenheit. Now, the reason why the temperature is very, very high at the center or the core of the sun is because of gravity. So the force of gravity trying to continuously squeeze the sun smaller is making the temperature 27 million degrees Fahrenheit at the core. Remember, when you compress a cloud of gas, you cause the cloud's temperature to go up. The second thing is, if you were down at this portion of the sun, you have the weight of all of the layers above you that gravity is trying to squeeze to the center. The force of gravity is trying to make the sun smaller. So it's trying to make all of this material be squeezed to the very center of the sun. So that creates a pressure of all of these outer layers, this pressure bearing down on the center of the sun. The sun is almost 1 million miles across. So you have nearly 500,000 miles of gas that the sun is squeezing tremendously to try to make it come down to the middle. So this creates a pressure that is 3 trillion pounds per square inch. Now, the reason why these two numbers are important, first of all, is because gravity is causing both of these numbers to be what they are. Gravity makes the sun very hot, and gravity makes the sun have this tremendous pressure at the center. And what this means is the sun's primary material, if you remember from a previous video, the sun is almost entirely made out of hydrogen, 91% hydrogen. What this means is under these conditions at the core, the hydrogen atoms are forced to do something that they normally don't or can't do. So there's a physics that the hydrogen atoms will undergo that is normally not what hydrogen will do. And that physics is called thermonuclear fusion. Now, before I go into the details, let's dissect the words a little bit. The word fusion means when you take separate things and you put them together into one single thing. So let's imagine that we have a nucleus of an atom, and let's say these are protons and these are neutrons, and here is a different nucleus of a different atom, again protons and neutrons. If this nucleus comes together with this nucleus and they come together to become one thing, that is called nuclear fusion, the fusion of nuclei. Now, why is it called thermonuclear fusion? Well, that becomes a little bit more complicated. The word thermo is the word that means temperature. So if you put all this together, thermonuclear fusion means the fusion of atomic nuclei because of temperature. So what that means is that inside of the sun, the nuclei of atoms are being forced together to become one thing, but it requires a very high temperature. And the reason for the high temperature is we're talking about hydrogen nuclei, and a hydrogen nucleus is just a proton. One proton by itself is the nucleus of hydrogen. A proton has a positive electrical charge. And if you take two protons and you get them closer together, the fact that they're both positively charged particles means that they're going to actually push each other apart. We call this electrostatic repulsion. When you have like charges, positive, positive, and you get them closer together, they start to push each other apart. Well, trying to get these protons to come together and fuse means you have to overcome the fact that they're trying to push each other apart. So how do you make protons come together and fuse when they're trying not to fuse because of their positive charges? What you do is you make the two protons come at each other with a collision course that is unavoidable. You send them on a journey that comes right at each other so that they can't avoid the collision because they're going so fast. The faster they go, the fact that they're going so fast means that they're going to have to collide whether they like it or not. So if you remember, temperature is the average velocity of atoms and molecules. So at a very high temperature, the protons come at each other with such a high speed that they're forced to fuse even though they're trying not to. You have put them on an unavoidable, basically a collision course that they can't overcome because of their positive charges. So ultimately what we get is the fusion of atomic nuclei because of the very high temperature. Hydrogen will only do this if the temperature is really, really high. And the minimum temperature for hydrogen to do this is about 2 million kelvins. Normally hydrogen in the water that we're drinking or swimming in, or the hydrogen that's in the environment of the Earth, hydrogen won't do this because it's not at a very high temperature. But inside of the sun, the hydrogen is at this enormous temperature, and so the hydrogen is forced to do what it just doesn't want to do. Now what I'm going to show you is how this works, so let me go to the next slide here. Inside of the sun, at the very core, the type of nuclear fusion that is occurring is called the proton-proton cycle. The reason why it's called this is because a single hydrogen nucleus is a proton. And so cycle means that it's repeating over and over and over again. This happens over and over and over every second of every minute of every hour of every day. Now this is the summary, and these are the details. The summary is 4 hydrogen nuclei fuse to become 1 helium nucleus plus 2 gamma ray photons. So 4 hydrogen nuclei fuse to become 1 helium nucleus plus 2 gamma ray photons. Let's look at the details. I admit this is quite complicated, but I just want you to see the essence of what's happening here. 2 hydrogen nuclei, 2 protons, come together and fuse. Now, when they're forced to slam into each other, this unavoidable collision, they fuse together and one of the protons transforms into a neutron. So we now have a proton and a neutron bound together. And in this reaction, the fusion reaction spawns what's called a neutrino and spawns what's called a positron, which is antimatter, both subjects for another day. Now, this is still hydrogen, still element number 1 because it has 1 proton. This is what we call a hydrogen isotope. An isotope is when you take a nucleus and you change the number of neutrons. So this has been given a neutron that it doesn't normally have, so it's a hydrogen isotope. Now this hydrogen isotope and another hydrogen nucleus somewhere else will also then slam into each other and a second round of fusion occurs. It's in this fusion reaction that we get these three subatomic particles to fuse together, and it also generates a gamma ray photon, a photon of light, goes whizzing off somewhere else. Now notice fusion has created light. The fusion result is this, which is called helium-3, which is a helium isotope. And so 2 protons, 1 neutron, makes it element number 2. Element number 2 is helium. Now we're not quite done yet. What happens is somewhere else in the sun, this is also happening many, many times over. And so eventually the helium isotope runs into and slams into another helium isotope. And when this occurs, the final stage of fusion is finished. We end up getting normal helium. This is actually stable, normal helium. But then 2 protons are now released to go back and start this all over again. So what you can see is that it's a cyclical process happening over and over and over again. And notice that we get 1, 2, 3, 4, 5, 6 hydrogen nuclei go in, 2 of them get returned, so ultimately 4 of them get used, and what you get out is a nucleus of helium. Hydrogen is becoming helium. Now, whenever we take one element and turn it into a different element, this is called nucleosynthesis. Nucleosynthesis is to turn one atomic element into a different atomic element. If you think about it, element number 1 on the periodic table is being turned into element number 2 on the periodic table. So this is not burning, this is not rearranging molecules, this is transforming the nucleus of the atom to become a different element, and in the process you give off light. So the light that the sun is pouring out is coming from the conversion of hydrogen into helium at the core of the sun. Now let's do a little bit of bookkeeping. If we were to look at the numbers, 4 hydrogen nuclei add up to this mass. Very tiny, tiny, tiny number. 6.693 times 10 to the minus 24. This is the collective mass of 4 protons, 4 hydrogen nuclei. It's very small. Now these 4 protons come together and fuse and ultimately become 1 helium nucleus. 4 hydrogens become 1 helium. But this is the mass of 1 helium nucleus. Notice the numbers look nearly identical. Both of them 10 to the minus 24, 6.6, but notice the 9.3 and the 4.5. So what this is saying is the 4 hydrogen nuclei become 1 helium nucleus, but the mass is different. In other words, what goes in comes out as a slightly lower mass. Now logically this doesn't make sense. If I take 4 of these things and put them together and they become this one big thing, the 4 of them together should equal the mass of the one big thing because you're just combining them together. But in reality, there's a small amount of mass that's missing. The difference of just this tiny, tiny little number works out to be less than 1%. Now the reason why that's critical is because that mass, that small amount of mass that's missing from the reaction, was the mass that was turned into the light. So our sun is turning hydrogen into helium, and some of that hydrogen is becoming helium, but some of the hydrogen is becoming light. So our sun makes the light that we see by converting hydrogen to helium, but some of the hydrogen becomes photons, and those photons leave the sun. So every moment of every day, the proton-proton cycle is happening, steadily converting hydrogen into helium to make the light that we see. This is a nuclear reaction, and it's a very exotic one that follows nuclear physics. Now, what we'll see in the next video is how this energy production maintains the life of the star, and eventually what happens when a star is no longer able to sustain this nuclear reaction and eventually runs out of the ability to produce energy. So I'll see you then.